if you enjoy drifting through questions like this, you're very welcome to subscribe and join these quiet explorations. And if it's not too much to ask, I'd love to know where you're watching from tonight. Quantum physics did not begin as an attempt to be strange. It emerged because careful measurements refused to agree with familiar rules. Heat behaved oddly. Light arrived in unexpected ways. Matter itself seemed unsure of where it was or how fast it moved. What followed was not a rejection of reality, but a deeper look at it, guided by patience, precision, and a willingness to let go of certainty. Over time, this quiet framework revealed a universe built not from definite outcomes, but from probabilities. A place where events are shaped by chance within firm boundaries, where observation matters, and where the act of looking is itself a form of interaction. The quantum world does not hide behind mystery for its own sake. It simply follows rules that feel unfamiliar to human intuition. Tonight's journey moves gently through that world, not to solve it, and not to force it into neat explanations, but to rest with its strangeness, to explore how reality behaves when certainty loosens, and to notice what it feels like to let questions remain open. Settle in, let the sharp edges soften, and allow the strange, quiet logic of the quantum world to unfold slowly. Quantum physics has a reputation for being strange, confusing, even unsettling. But when approached slowly, it becomes something else entirely. It becomes a story about limits, uncertainty, and the surprisingly gentle rules that govern the smallest pieces of reality. A story that does not demand answers, only attention for as long as it feels comfortable. So as the world outside grows quieter and thoughts begin to soften at the edges, here is a question to carry gently into the night. What if the universe, at its deepest level, is not built from solid things at all, but from possibilities quietly waiting to become real? At the end of the 19th century, physics felt settled in a way that is difficult to recapture now. The universe appeared orderly and cooperative, governed by laws that were not only reliable but reassuringly smooth. Motion followed clean paths, heat flowed in predictable directions, light behaved as a wave, spreading gently through space according to equations that had been tested again and again. There was a sense, quietly shared among many physicists, that the great structure of reality had already been uncovered, and that what remained were refinements rather than revelations. This confidence did not arise from complacency. It grew out of extraordinary success. Classical physics explained the workings of engines and bridges, the behavior of gases, the ticking of clocks, and the motion of planets with remarkable precision. It powered industries, illuminated cities, and gave the impression that nature, once mysterious, had finally agreed to be understood. With enough patience and careful calculation, it seemed that almost any physical question could be answered. Almost. The first sign of trouble did not arrive with a dramatic contradiction or an exotic experiment. It appeared in a place so familiar that it barely raised suspicion at all. It began with warmth. When an object is heated, it begins to glow, at first faintly, then more intensely as the temperature rises. Iron turns red, then orange, then white. Coals brighten, filaments shine. This glow is not decorative. It is radiation, emitted as the vibrating atoms within the object release energy into their surroundings. The relationship between temperature and emitted light was easy to observe and seemed, on the surface, easy to explain. This behavior was known as blackbody radiation. Classical physics approached the problem with confidence. Heat was energy, and energy was something the equations handled well. As temperature increased, more energy should be available to radiate away. The mathematics suggested that hotter objects would emit more light at higher frequencies, shifting steadily towards shorter wavelengths as the temperature rose. When the calculations were carried through fully, however, the results became impossible to ignore. According to the equations, the energy emitted at very high frequencies should increase without limit. As wavelengths grew shorter and shorter, the predicted radiation surged upward, racing toward infinity. The mathematics did not merely disagree with experiment. It produced results that could not exist in the real world. infinite energy, not as a poetic exaggeration, but as a literal outcome of the formulas themselves. Nothing in nature behaved this way. No heated object unleashed endless radiation. The equations were internally consistent, yet profoundly wrong in their conclusions. The mismatch was so stark that it earned a blunt name: the ultraviolet catastrophe. Physicists tried to fix it without abandoning familiar ideas. They refined assumptions, adjusted models, and scrutinized experimental setups. But no amount of careful tuning could rescue the predictions. The failure did not come from careless measurement or flawed logic. It came from pushing classical ideas into a regime where they no longer applied. Something about the picture of energy itself was breaking down at very small scales. For a time, this failure lingered as an irritation rather than a crisis. It was uncomfortable, but it was also isolated. The rest of physics worked too well to suggest that the entire framework was in danger. Surely this was a technical problem, solvable with the right mathematical insight. Then Max Planck entered the story. Planck was not a revolutionary by temperament. He was methodical, cautious, and deeply committed to the classical worldview. He did not believe that physics required a fundamental overhaul. His aim was modest and practical. He wanted the equations describing blackbody radiation to match what experiments were clearly showing. Faced with mathematics that refused to behave, Planck made an unusual move. Instead of adjusting the equations further, he adjusted the assumptions beneath them. What if energy could not be exchanged in arbitrary amounts? What if it arrived in discrete steps? Rather than flowing smoothly like water from a tap, energy might be transferred in tiny packets, each with a fixed size. You could add them together, but you could not divide them endlessly. The image was closer to counting coins than measuring liquid. This idea was introduced not as a claim about reality, but as a formal device. Planck treated it as a mathematical convenience, a way to force the equations into agreement with observation. To make the numbers work, he introduced a small constant that set the scale of these packets. Its value was extraordinarily tiny, so small that it seemed unlikely to matter beyond this specific problem. When Planck recalculated the radiation curve using this assumption, the catastrophe disappeared. The predictions aligned with experiment. The runaway energy was gone. The curve bent gently instead of exploding upward. The equations finally matched the real world. Planck had solved the ultraviolet catastrophe. And yet, he did not trust the solution. Planck himself regarded quantization as a temporary patch, not a fundamental truth. He believed that a deeper explanation would eventually restore continuity to physics and render his assumption unnecessary. The universe, he felt, surely did not operate in abrupt, jerky steps. The packets were scaffolding, not structure. From a modern perspective, it is tempting to view this moment as the birth of quantum theory, a dramatic turning point in the history of science. But at the time, it felt far less significant. There were no bold proclamations, no sense that certainty had cracked. There was simply a problem that had been fixed in the most economical way possible. Planck published his result quietly, as a careful piece of mathematical work. Others took note, appreciating that the equations now behaved. Few immediately grasped the deeper implications. After all, classical physics still worked beautifully in almost every other context. The interpretation could wait. But the assumption could not be confined to one corner of physics for long. If energy exchange was quantized in heated objects, why not elsewhere? Why should atoms absorb and emit energy smoothly if radiation did not? Why should light interacting with matter respect continuity when heat did not? Gradually, similar patterns began to appear in other experiments, hinting that Planck's reluctant assumption might reflect something real. The failure of classical ideas at small scales was not a failure of intelligence or effort. It was a failure of extrapolation. Concepts shaped by everyday experience had been extended beyond their natural limits. At human scales, energy changes appear smooth because the steps are too small to notice. At very small scales, those steps mattered. The universe, it seemed, was keeping count. This counting did not disrupt daily life. Heat still flowed, light still glowed. The world remained solid and predictable. But beneath that smooth surface, the assumption of infinite divisibility had been quietly set aside. Planck himself remained cautious for years, resisting more radical interpretations. Others would take those steps instead, applying the idea of quantization more broadly and discovering that it fit far more of nature than anyone had expected. At this early moment, though, none of that was obvious. There was only a glow that refused to behave, equations that misbehaved in response, and a careful physicist who adjusted the rules just enough to make sense of the measurements. The first crack in reality did not announce itself loudly. It appeared as a small assumption, tucked into a calculation that erased an impossible result. Physics did not collapse that day, but it did for the first time admit that its smooth picture of the universe had limits. Light has always felt gentle. It fills rooms without asking permission, slips through windows, and quietly makes the world visible. Long before anyone tried to describe it with equations, light was treated as something smooth and continuous, more like a ripple spreading across water than a collection of individual things. By the late 19th century, this intuition had hardened into certainty. Light was understood as a wave, and a remarkably well-behaved one. It bent, it spread, it interfered with itself, and every careful experiment seemed to confirm that picture. Classical physics was very comfortable here. Waves were familiar territory. Water waves, sound waves, vibrations along a string, all behaved in ways that could be captured cleanly by mathematics. Light fit neatly into that family. Its color depended on frequency. Its brightness depended on intensity. Make the wave taller and the light grows brighter. Change the frequency and the color shifts. The relationship felt natural, almost obvious. The trouble began when physicists stopped asking how light moved through space and started asking how it interacted with matter. One experiment in particular refused to cooperate no matter how carefully it was performed. It involved shining light onto a metal surface and observing what happened to the electrons inside. Under the right conditions, electrons would be ejected from the metal, springing free as if nudged loose by the incoming light. This became known as the photoelectric effect. At first glance, it seemed straightforward. Light carries energy. Energy transfers to electrons. Electrons escape, increase the brightness of the light, and more energy should be delivered. That expectation turned out to be wrong. What experiments revealed was strangely precise. Below a certain frequency of light, no electrons were emitted at all. It didn't matter how bright the light was. The metal remained unaffected. Turning up the intensity changed nothing. The electron stayed firmly in place. Then, increase the frequency slightly. Even if the light is faint and electrons are released immediately, there is no waiting period, no gradual build-up. The effect either happens at once, or it does not happen at all. This behavior was deeply uncomfortable for the wave picture of light. If energy arrived continuously, dim light should still deliver energy, just more slowly. Given enough time, electrons should eventually absorb enough energy to escape. But time did not help. Brightness did not help. Only frequency mattered. It became clear that brightness and energy were not the same thing. Into this puzzle stepped Albert Einstein. In 1905, Einstein was a young physicist working in a patent office, far from the centres of academic authority. He had been thinking carefully about Max Planck's earlier work on blackbody radiation, and in particular about the strange suggestion that energy might be exchanged in discrete packets. Planck himself had treated that idea cautiously, almost apologetically, but Einstein recognized that it might reach further than anyone expected. What if light itself arrived in packets, not just energy exchanged during heating, but light as it interacted with matter? Instead of a smooth wave delivering energy gradually, light might come in individual bundles, each carrying a fixed amount of energy determined by its frequency. With that shift, the photoelectric effect fell neatly into place. Brightness now controlled how many packets arrived, not how energetic each one was. A bright low-frequency light delivered many packets, but each packet carried too little energy to free an electron. No matter how many arrived, none would succeed. A dim, high-frequency light delivered fewer packets, but each one carried enough energy to do the job. One interaction was enough. The electron did not slowly accumulate energy. It received it all at once or not at all. Einstein referred to these packets as light quanta, a deliberately cautious name that avoided claiming too much. Later, they would be called photons, but even that word can mislead if taken too literally. A photon is not a tiny marble racing through space. It is not a miniature particle in the everyday sense. It is better understood as the smallest possible exchange of light energy, a single, indivisible interaction between light and matter. Light can still spread like a wave while it travels. It can diffract, interfere, and overlap with itself in ways that only waves can. But when it gives up energy, it does so in whole steps. No fractions, no partial exchanges. Once again, the universe reveals a preference for counting. This did not overturn the wave picture of light. Interference patterns still appeared, diffraction still occurred. The wave description remained essential, but it was no longer sufficient on its own. Light behaved like a wave when it moved through space, and like a collection of packets when it interacted with matter. Both descriptions were necessary, each illuminating a different aspect of the same phenomenon. Einstein's proposal was bold, but it was grounded firmly in experiment. The photoelectric effect behaved exactly as the packet idea predicted, and further tests continued to confirm it. In 1921, Einstein was awarded the Nobel Prize in Physics, not for relativity, but for this explanation of how light ejects electrons from metal surfaces. Light, it turned out, didn't merely flow. It arrived. This distinction quietly reshaped physics. Brightness came to mean quantity. Frequency came to mean capability. One determined how many interactions occurred, the other determined what those interactions could accomplish. Once seen clearly, the difference could not be ignored. In everyday life, nothing seemed to change. Lamps still glowed smoothly. Sunlight still warmed skin. Light still appeared continuous. The packets were too small, the steps too fine, to notice without careful experiments. But beneath that smooth surface, the counting continued. Each interaction between light and matter occurred as a discrete event, precise and indivisible. Each freed electron testified to a simple rule that nature appeared unwilling to bend. Energy arrives in steps, and light, however gently it may appear to flow, keeps track of every one of them. At first glance, the double-slit experiment looks almost too simple to matter. A source of light, a barrier with two narrow openings, and a screen placed behind it to catch whatever makes it through. Nothing about the setup suggests that it should unsettle centuries of intuition. It feels more like a tidy classroom demonstration than a moment that would quietly reshape how reality is described. And yet, this modest arrangement turned out to be one of the most revealing experiments ever performed. To understand why, it helps to begin with waves, because waves were exactly what everyone expected to see. When a wave passes through a narrow opening, it spreads out. Water waves do this. Sound waves do it too. Light waves, long understood to behave in the same way, also spread as they pass through gaps. If there are two openings instead of one, the waves emerging from each overlap with one another, sometimes reinforcing each other, sometimes cancelling out. This overlapping produces a pattern of alternating bright and dark regions known as interference. On a screen, it appears as a series of evenly spaced bands, a visual fingerprint that waves leave behind wherever they meet and mix. When light is shone through two narrow slits, this interference pattern is exactly what appears. Not two bright patches behind the slits, but many bands stretching across the screen. The result is so clear and repeatable that it leaves little room for doubt. Light is behaving like a wave. For a while, that seemed to be the end of the story. The puzzle only deepened when physicists asked what would happen if the light were made extremely faint. Instead of a steady beam, imagine sending light toward the slits one photon at a time, with long pauses in between. Each photon arrives alone, with no neighbours close enough to interact with in any ordinary sense. If light were truly behaving as a stream of particles, the expectation would be simple. Each photon would pass through one slit or the other, strike the screen, and leave a single dot. Over time, those dots should form two loose clusters aligned with the slits. That is not what happens. When the experiment is performed this way, the screen does fill with dots, one by one, each arrival separate and unremarkable. But as the dots accumulate, a familiar structure slowly emerges. Bright regions where many dots appear, dark regions where almost none do. The same interference pattern seen with a continuous beam. A wave pattern built patiently out of individual events. This result is difficult to absorb at first. Each photon arrives on its own. There's nothing else present to interfere with, and yet the overall distribution looks exactly as if waves had passed through both slits and overlapped with themselves. Somehow, each photon contributes to a pattern that seems to require the presence of many at once. The natural question follows almost immediately. How does a single photon know where to land? It does not behave like a tiny marble choosing a single path and a single destination. Instead, it behaves as if its behavior between emission and detection is described by a range of possibilities. The photon does not travel along one definite route in the everyday sense. It evolves in a way that allows many potential outcomes, each with its own likelihood. The interference pattern is not created by photons interacting with one another. It is created by the structure of those possibilities. So far the behavior is strange, but still manageable. The rules are unfamiliar, but they are consistent. The real tension appears when the experiment is altered in a subtle way. A detector is placed near the slits, capable of determining which opening each photon passes through. Nothing else is changed. The light source remains the same. The screen remains the same. Only the possibility of knowing the path is introduced. The effect is immediate and unmistakable. The interference pattern disappears. In its place, two simple regions form on the screen, corresponding to the two slits. The photons now behave exactly as particles are expected to behave, each arriving in a way that reflects a single, definite path. Remove the detector and the interference returns. Restore it, and the pattern vanishes again. The shift is sharp, not gradual. At first glance, this can sound as though reality itself is responding to being watched, as if the photon somehow knows when it is under observation and changes its behavior accordingly. That interpretation is tempting, but it misses something important. What matters is not awareness. What matters is interaction. To determine which slit a photon passes through, the photon must interact with something physical. That interaction links the photon to the measuring device, and, through it, to the surrounding environment. In doing so, it alters the conditions that allow the different possibilities to overlap and interfere. When no path information exists, the photon's behavior is described by a broad range of overlapping possibilities. When path information exists, even in principle, those possibilities are narrowed. The overlap is lost, and with it, the interference pattern. The universe is not responding to curiosity, it is responding to contact. This distinction helps explain why the result feels so counterintuitive. Everyday experience trains the mind to expect objects to have definite positions and paths at all times. A thrown ball follows a trajectory. A dropped key falls straight down. There is no sense in which those objects explore multiple possibilities before settling on one. At very small scales, that intuition no longer applies. In the double-slit experiment, the interference pattern is not a picture of individual photons weaving intricate paths through space. It is a map of likelihoods, a record of where photons are more or less likely to arrive when the system is allowed to evolve freely. Each detection event taken on its own looks entirely ordinary, just a single dot on a screen. But taken together, those events reveal a deeper structure that only appears when constraints are removed. It is a bit like watching rain fall on a pavement. One drop tells you very little. Thousands of drops reveal the outline of the roof above. Measurement in this setting is not passive. It is not simply reading off a pre-existing fact. It is an active physical process that changes the system being measured. By asking a more specific question, the system is forced into a more specific state. Specificity comes at a cost. When left alone, light explores many possibilities at once. When constrained, it commits to one. This does not mean that reality is vague or incomplete until someone looks. It means that, at small scales, Some properties do not exist in sharply defined form until interaction makes them so. The double-slit experiment does not suggest that the universe is irrational or chaotic. Its behavior is precise, consistent, and repeatable. The same setup produces the same statistical pattern every time. The rules are clear, even if they are not the ones intuition expects. Interference is the clue that something wave-like is always present in the background, even when individual events appear particle-like at the moment of detection. Measurement reveals one outcome, but the pattern emerges from many. The lesson is not that light is confused about what it is that the categories of wave and particle are tools, not truths. Useful descriptions that work in some situations and quietly fail in others. When light moves freely, it behaves as if it is everywhere it could be. When it is forced to account for itself, it behaves as if it has always been somewhere specific. Both descriptions are accurate within their limits. Neither tells the whole story on its own. Left alone, reality is generous with possibilities. When pressed for an answer, it responds with a single, definite outcome. And in the space between those two behaviors lies the quiet strangeness that the double-slit experiment continues to reveal. As the strange results of experiments continue to accumulate, it became clear that physics needed a new way of speaking. Not just new ideas, but a new kind of language altogether. Light behaved like waves until it did not. Particles left individual marks while somehow building wave patterns. The familiar tools of classical motion, neat paths traced through space and time, were no longer enough to describe what was being seen. What was missing was not intuition, but structure. That structure arrived in the form of a mathematical framework developed by Erwin Schrödinger, a physicist who hoped, perhaps optimistically, to restore some sense of continuity to the quantum world. His aim was not to make reality stranger, but to describe it more gently, using smooth change rather than abrupt jumps wherever possible. What emerged from this effort was an equation that would become central to quantum physics, not because it offered easy answers, but because it offered a consistent way to track how quantum systems evolve. It is often called Schrödinger's equation, but thinking of it as a formula to be solved misses its real role. It is better understood as a set of instructions. Given a quantum system as it is now, the equation tells how that system changes over time, not where a particle will be found and not what outcome will occur, but how the range of possibilities reshapes itself moment by moment. At the heart of this description lies the wave function. Despite its name, the wave function is not a physical wave rippling through space. It does not slosh or vibrate or carry substance from one place to another. It is a description, a compact mathematical summary of everything that can be said about a system's possible states. Where a particle might be found, how likely each possibility is, which energies are allowed, which outcomes are forbidden. The wave function does not tell a particle where it is, it tells the universe where the particle could be. This shift is subtle but profound. In classical physics, motion is described as a sequence of positions. At each moment, an object occupies a specific point in space and moves smoothly to the next. Given enough information, the entire path can be traced in advance. Uncertainty, when it appears, usually reflects missing knowledge rather than a limitation of nature itself. In the quantum world, that picture dissolves. Instead of a single path, a particle is described by a spread of possibilities, a probability cloud rather than a line. Some regions are more likely than others, but none are guaranteed until an interaction occurs. Between measurements, the particle does not travel from one definite place to another in the familiar sense. Its wave function evolves, reshaping the landscape of likelihoods as time passes. This does not mean the particle is vague or ill-defined. It means the description has changed. Precision now applies to probabilities rather than positions. Schrödinger's equation governs how these probability clouds move and change. It tells how they spread, how they shift, how they interfere with themselves, and how they respond to forces. Importantly, it does all of this smoothly. There are no sudden jumps in the evolution of the wave function itself. The mathematics is calm, continuous, and exact. The uncertainty appears only when a specific outcome is demanded. This distinction is often overlooked. Quantum physics is not unpredictable because its laws are sloppy. The laws are precise to an extraordinary degree. Given a wave function, its future evolution can be calculated exactly. What cannot be predicted is which single outcome will be realized when a measurement takes place. That randomness is not a flaw, it is a feature. To make sense of this, it helps to think again in terms of clouds rather than paths. Imagine releasing a faint mist into still air. At first, it is concentrated in one place. Over time, it spreads, thinning in some regions and thickening in others depending on subtle currents. The mist does not follow a line. It occupies a region with varying density. A probability cloud behaves in a similar way. Where the cloud is denser, the particle is more likely to be found. Where it is thinner, less likely. But until interaction occurs, the cloud itself is the most complete description available. When a measurement happens, the cloud does not slowly narrow. It resolves into a specific outcome. The particle is found in one place, with one value of energy or motion. The probabilities have done their job. One possibility has been realized. Before that moment, asking for a precise position is like asking for the exact location of a sound before it is played. The question does not yet apply. This reimagining of motion can feel unsettling because it challenges deeply ingrained habits of thought. Everyday experience insists that objects are always somewhere, moving along well-defined routes whether anyone looks or not. That intuition works beautifully at large scales, where probability clouds are so tightly packed that they behave like solid points. At small scales, the clouds are wider, and their spread can no longer be ignored. The wave function does not represent ignorance. It represents completeness. It is not hiding a secret path behind a curtain. It is telling the full story that nature allows at that scale. Trying to force a sharper picture onto it does not reveal more truth. It introduces confusion. This is why it matters to treat the wave function as a description, not an object. It is not something a particle carries around. It is not a physical mist-filling space. It is a rule book for how possibilities behave. Different interpretations of quantum physics disagree about whether the wave function should be considered real in some deeper sense, but all agree on its practical role. It works. It predicts experimental results with astonishing accuracy. It explains why atoms are stable, why certain energies appear and others do not, and why particles can behave in ways that no classical object ever could. Most importantly, it replaces the idea of fixed paths with something more flexible. Motion, at the smallest scales, is no longer about tracking where something is at every instant. It is about tracking how likelihoods flow. A particle moves not because it follows a line, but because the center of its probability cloud shifts. Its behavior emerges from the changing shape of possibility itself. In many situations, these clouds remain tightly confined. Their motion closely mimics classical trajectories, which is why the everyday world feels so solid and predictable. In other situations, the clouds spread, overlap, and interfere, producing effects that have no classical counterpart. The mathematics allows for both, without contradiction. Schrödinger himself hoped that this wave-based picture would soften the harsher edges of quantum theory, restoring a sense of continuity that the idea of sudden collapses seemed to threaten. In some ways, it does. The evolution of the wave function is gentle, lawful, and smooth. The strangeness enters not through the mathematics, but through what is asked of it. When no specific outcome is required, the universe is content to carry many possibilities at once. When an outcome is demanded, one is selected and the rest fall away. The mathematics does not say why that particular outcome occurs, only how likely it was. This is not a failure of explanation. It is a statement about the structure of reality. At the smaller scales, the universe does not commit itself to a single story until interaction forces the issue. Until then, it moves through a space of possibilities, guided by precise rules that favor some outcomes over others. Solid paths give way to probability clouds. Deterministic motion gives way to evolving likelihoods. What replaces certainty is not chaos, but a quieter, more subtle order. The mathematics of possibility does not strip meaning from the world. It reshapes it, and in doing so, it offers a picture of motion that is less rigid, more flexible, and in its own way, deeply elegant. By the time quantum ideas had begun to settle into a workable framework, a new discomfort made itself known. Even with careful mathematics and beautifully predictive equations, there remained a sense that something fundamental was slipping through the fingers. Not a gap in knowledge that better tools might fix, but a limit that refused to move no matter how gently it was approached. This limit became known as the uncertainty principle, and it has been misunderstood almost from the moment it was introduced. At first hearing, it sounds like a confession of failure, a statement that measurements are clumsy, that instruments interfere too much, that precision is lost because the act of looking gets in the way. Shine light to see a particle, and the light knocks it about. Try to pin down its motion, and the act of pinning disturbs it. From this point of view, uncertainty feels like an engineering problem waiting for a better solution. But that explanation, comforting as it may be, misses the point. The uncertainty principle is not about limitations of technology, and it is not about careless measurement. Even in a perfectly quiet universe, with perfect instruments and infinite patience, the uncertainty would remain. It is not imposed from the outside. It is woven into the structure of nature itself. To understand why, it helps to think again in terms of waves and probability clouds, rather than solid points. A particle described by a wave function does not occupy a single location. Its presence is spread out, more here, less there, with no sharp boundary. That spread is not a blur caused by ignorance. It is the most complete description available. Now imagine trying to squeeze that spread into something narrower. The more tightly the cloud is confined in space, the more complicated its internal structure must become. It begins to include a wider range of motions. Precision in position comes at the cost of precision in motion, not because something has gone wrong, but because waves behave that way. This trade-off is unavoidable. It is not a statement about what can be known. It is a statement about what can exist. Trying to specify both position and motion with perfect accuracy is like trying to describe a melody using a single instant of sound. The request itself asks for more than the phenomenon can provide. The universe does not store that information because it is not part of how things are organized. This is why the uncertainty principle feels so different from everyday experience. In daily life, objects appear to have definite positions and definite motions at all times. A car moves down a road, a thrown stone follows a clear arc. Nothing seems blurry or ambiguous. But those objects are made of vast numbers of particles. Their individual uncertainties overlap and average out, producing behavior that appears crisp and deterministic. The blur is still there, but it is buried beneath scale. At small scales, there is nowhere for it to hide. A helpful way to picture this is fog. Standing in thick fog, it is possible to tell roughly where something is, but not precisely. Move closer, and its position becomes clearer. At the same time, its direction of motion becomes harder to judge. Step back, and the direction becomes clearer, but the position softens again. There is no single vantage point where everything snaps into perfect focus. The fog is not hiding something sharp. The fog is the situation. Or consider touch. Trying to locate a delicate object with bare hands often requires compromise. Press gently, and its exact position is uncertain. Press firmly, and its motion changes. There's no way to extract perfect information without altering the state of what is being touched. The uncertainty principle expresses this kind of balance, elevated from everyday experience to a fundamental rule. One of the most important consequences of this rule is that it rules out certain classical fantasies entirely. There is no hidden ledger beneath the surface where every particle carries an exact position and an exact motion at all times, waiting to be revealed. The uncertainty is not about missing information. It is about the absence of that information altogether. Nature refuses that level of precision. This refusal is not sloppy or approximate. The uncertainty principle is exact. The boundary it draws is sharp and unyielding. It does not say that nothing can be known. It says that some pairs of properties cannot be defined simultaneously beyond a certain limit, because defining one necessarily loosens the other. Within that limit, quantum physics remains astonishingly predictive. The probabilities it assigns are precise. The patterns it forecasts are reliable. What it does not offer is certainty about individual outcomes, and it never promises to. This built-in blur reshapes how motion itself is understood. In the quantum world, motion is not the steady sliding of a point along a path. It is the evolution of a distribution, a shifting pattern of likelihoods that flows and reshapes itself over time. A particle moves because its probability cloud moves. The center of that cloud drifts. Its shape may stretch or compress. But it never collapses into a perfectly sharp point while retaining a perfectly sharp motion. This blur is not a flaw to be corrected. It is what allows the quantum world to function at all. Without it, atoms would not be stable. Electrons would collapse into nuclei. Matter would lose its structure. Chemistry would fail. Biology would never emerge. The uncertainty that feels so uncomfortable at first glance turns out to be the quiet guardian of complexity. There is a strange kindness in that. What appears as a restriction is actually a protection. The blur prevents the universe from becoming too rigid, too brittle. It allows systems to settle into stable arrangements rather than spiraling into extremes. This does not mean the world is fuzzy everywhere. At large scales, the uncertainty becomes vanishingly small. The fog thins. Paths reappear. Classical physics takes over, not because quantum rules stop applying, but because their consequences are drowned out by scale. At small scales, the fog remains thick. The uncertainty principle does not say that reality is unknowable. It says that reality is structured in a way that resists absolute sharpness. Some questions simply ask for more precision than nature is willing to provide. Once that is accepted, the principle stops feeling like a barrier and starts feeling like a guide. It tells where classical intuition can be trusted and where it must be softened. It marks the boundary between solid expectations and a more fluid way of thinking. The built-in blur is not an error to be fixed, it is a feature to be understood. It is the quiet softness at the heart of the quantum world, ensuring that nothing is ever pinned down too tightly, and that possibility always has room to move. One of the most persistent ideas in everyday thinking is that things must always be one way or another, here or there, moving or still, on or off. It feels natural to assume that reality makes up its mind immediately and then sticks with the decision. At large scales, that assumption works beautifully. At very small scales, it quietly falls apart. In quantum physics, systems do not rush to choose. They linger in a state of possibility, carrying several potential outcomes at once. This behavior is known as superposition, and despite its reputation for sounding mystical or absurd, it is best understood as something calm, practical, and deeply ordinary once the right picture is in place. Superposition does not mean that a particle is confused, conflicted, or half-finished. It means that, before interaction demands a specific answer, the system is described by more than one allowed state at the same time. These states coexist, each weighted by how likely it is to appear when the moment comes. This coexistence is not a failure to decide, it is the natural default. To see why, it helps to return to the idea of the wave function. The wave function does not point to a single outcome. It describes a spread of possibilities, each one mathematically present and evolving smoothly over time. As long as the system is left alone, nothing inside the mathematics forces one possibility to be selected over the others. There is no hidden clock counting down to a decision. The system does not choose because nothing requires it to. In classical physics, change is driven by forces acting on objects with definite properties. Push something, and it moves. Pull it back, and it slows. The present determines the future in a continuous chain. In the quantum picture, the rules are different. The wave function evolves according to precise laws, but those laws govern probabilities, not outcomes. As time passes, the distribution of possibilities shifts, stretches, and reshapes itself. Some outcomes become more likely, others fade. But until interaction occurs, all allowed outcomes remain part of the description. This is what superposition really means. It is the coexistence of futures. A quantum system can be in a superposition of positions, meaning there are several places it could be found. It can be in a superposition of energies, meaning it does not possess a single definite energy until interaction demands one. These are not vague states. They're sharply defined sets of possibilities, each with its own mathematical weight. The outcomes themselves are never blurry. When a result appears, it is always definite. The blur exists only in the range of options before that moment. This distinction matters because it dissolves many common misunderstandings. A particle in superposition is not smeared halfway across space in a physical sense. It is not partly here and partly there, like paint dragged across a canvas. It is fully capable of being found in several different places, and until interaction occurs, none of those possibilities has been excluded. Measurement is where the narrowing happens. When a quantum system interacts with something large enough to register an outcome, the range of possibilities contracts. One option becomes real, the others fall away. This is often described as collapse, but that word can suggest something violent or dramatic, as if reality were shattering into place. In practice, the process is quieter. Measurement does not create an outcome from nothing. It selects one from the set that already existed. The system does not invent a new property at the moment of interaction. It reveals one that was already allowed. A helpful way to think about this is to imagine a wide beam of light passing through an adjustable opening. Before the opening, the light spreads broadly. After it, the beam is constrained. The light itself has not changed its nature. The range of paths it can take has simply been limited. Measurement works in much the same way. It narrows what is possible. This perspective removes the temptation to think of observation as magical or consciousness-driven. Nothing waits for awareness. Nothing snaps into place because it is noticed. What matters is physical interaction. When a system becomes linked to its surroundings in a way that records an outcome, the superposition can no longer be maintained. The universe does not demand an answer until it has to. This reluctance to choose is not a flaw. It is an advantage. By allowing multiple possibilities to coexist, quantum systems can behave in ways that would otherwise be impossible. Interference patterns arise because overlapping possibilities can reinforce or cancel one another. Tunneling occurs because the range of allowed states includes outcomes beyond barriers that classical objects cannot cross. Atomic stability emerges because electrons exist in superpositions that spread them out rather than forcing them into precise orbits. Without superposition, the quantum world would be brittle. Systems would collapse into extremes. Structure would be lost. Even technologies that now feel cutting edge rely on this quiet feature. Quantum computing, for example, takes advantage of systems that can carry multiple potential answers forward at the same time. The power does not come from speed alone, but from breadth, from allowing many possibilities to evolve together before narrowing them down. Nature has been doing this long before humans noticed. Photosynthesis appears to exploit superposition to move energy efficiently through complex molecular structures. Certain biological processes seem to maintain quantum coherence just long enough to gain an advantage. These effects are subtle and delicate, but they point to the same underlying principle. Keeping options open can be useful. At larger scales, this behavior becomes difficult to see because interaction happens constantly. Air molecules collide, light scatters, heat flows. Superpositions are narrowed almost immediately, leaving only one outcome visible. This is why everyday objects appear definite and stable. They are never isolated long enough to remain otherwise. At small scales, where isolation is possible, the openness remains. Superposition is often described as strange because it conflicts with habits formed in a classical world. But strangeness is not the same as incoherence. The rules governing superposition are precise, testable, and reliable. Experiments confirm them again and again. The discomfort comes from expectation, not from behavior. The universe does not insist on being one thing at a time. It allows itself to be many things until interaction demands a choice. This generosity of possibility is not chaos. It is structured, weighted, and guided by exact laws. Once that is understood, superposition stops feeling like a paradox and starts feeling like a design choice. Reality does not hurry. It does not rush towards certainty. It carries its options forward calmly, letting them evolve, overlap, and influence one another until a boundary is imposed. Only then does it choose, and when it does, the choice is clean, definite, and final, not because the other possibilities were never there, but because their time has passed. Being many things at once is not a mistake. It is how the quantum world makes room for complexity, stability, and change all at the same time. Distance feels authoritative in everyday life. Two objects close together can influence one another easily. Two objects far apart cannot. Space separates, delays, and protects causality. This expectation is so deeply ingrained that it rarely feels like an assumption at all. It feels like a fact. At the quantum level, that confidence begins to soften. When two quantum systems interact in certain ways, they can become linked so thoroughly that describing one without the other no longer makes sense. Their properties stop belonging to them individually and begin to belong to the pair as a whole. This linking is called entanglement, and it is not about mysterious forces reaching across space. It is about relationships that refuse to break when distance is introduced. To understand entanglement, it helps to stop thinking in terms of individual objects and start thinking in terms of shared descriptions. In classical physics, systems carry their own properties wherever they go. After two objects interact and separate, each continues on with its own independent state. Any connection that existed between them ends at separation. Quantum systems do not always behave this way. When two particles interact and become entangled, the wave function that describes them no longer splits neatly into two separate parts. Instead, there is a single description that applies to both together. Certain properties remain undefined individually, but the relationship between them becomes sharply defined. This is the heart of entanglement. The particles do not each carry complete instructions. The instructions are shared. Imagine preparing two particles in such a way that when one is found to have a particular property, the other must have a corresponding one. The specific outcomes are not fixed in advance, but the correlation is, whatever happens here must be consistent with whatever happens there. Once the particles move apart, that correlation remains intact. This is where discomfort begins to creep in. If one particle is measured and a result is obtained, the outcome for the distant particle is immediately constrained. The shared description updates. It can feel as though information has travelled instantly from one location to another, as though space itself has been bypassed. This impression troubled Albert Einstein deeply. Einstein was not opposed to quantum mechanics as a predictive framework. He helped build it. But he was uneasy with any picture of reality that seemed to allow influences without mediation through space. For him, locality mattered. Causes should not leap across distance. Nothing should outrun light. Entanglement appeared to challenge that principle. Einstein famously referred to it as a kind of spooky action at a distance, not as a compliment, but as a warning. Something about the theory, he felt, was incomplete, and yet careful examination shows that entanglement does not violate relativity. The key is understanding correlation without communication. When a measurement is made on one member of an entangled pair, the outcome is random. It cannot be chosen or controlled. The same is true for the distant particle. Its outcome is not caused by the measurement elsewhere. It is constrained by the shared structure of the entangled state. No message is sent. No signal travels. No information is transmitted in a way that could be used to communicate faster than light. The apparent instant update occurs in the description of the pair, not in physical space. Until the results from both locations are compared, which requires ordinary communication limited by the speed of light, nothing observable distinguishes entanglement from chance. The correlations only reveal themselves when data from both sides are brought together. Relativity remains intact. This distinction is subtle but essential. Entanglement does not allow control at distance. It allows consistency at a distance. The universe ensures that outcomes fit together properly, even when they are separated by vast stretches of space. It does this not by sending messages, but by never assigning independent properties in the first place. The correlation was built in from the start. A common way of explaining this uses the idea of paired objects prepared together and then separated. If one is found to have a certain feature, the other must have the complementary one. The everyday version of this story often involves gloves placed in boxes and sent far apart. Open one box and the contents of the other are immediately known. But that analogy only goes so far. In the glove example, the properties were fixed in advance. One glove was always left-handed, the other right-handed. The information existed all along. In quantum entanglement, the outcomes are not predetermined in that way. The universe commits to the relationship without committing to the individual values until measurement occurs. Consistency is guaranteed, but specifics are left open. This is what unsettled Einstein. He suspected that hidden details must exist beneath the surface, quietly assigning definite properties ahead of time. Over the years, experiments were designed to test this possibility. Again and again, the results favored the quantum description. Nature appeared to resist being reduced to hidden classical instructions. Entanglement is not rare or exotic. It arises naturally whenever quantum systems interact and then separate without completely losing coherence. It plays a role in the structure of atoms, in chemical bonding, and in the collective behavior of particles and solids. It is not an anomaly. It is part of the fabric of the quantum world. It has also become a practical resource. Technologies such as quantum cryptography rely on entanglement to ensure security. Any attempt to intercept or copy an entangled system disturbs it in detectable ways. The same relational structure that once seemed philosophically troubling becomes, in this context, extremely useful. What makes entanglement powerful is not mystery but limitation. The impossibility of copying entangled states and the impossibility of controlling outcomes at a distance are not bugs. They are features that protect the integrity of the correlations. Seen this way, entanglement does not undermine causality. It reframes it. Cause and effect still respect the speed of a light. What changes is the idea that systems must always carry their own independent properties. At small scales, reality appears to be organized around relationships first, with individual attributes emerging only when interaction demands them. Distance in this picture is not the ultimate divider. Two particles that were once connected can remain part of a single description even when space grows between them. Their separation does not erase the history of their interaction. The universe remembers how they were linked. Entanglement does not suggest that everything is secretly connected to everything else. It suggests that when connections exist, they matter deeply, and they do not dissolve simply because objects move apart. The discomfort surrounding entanglement often comes from trying to force it into classical categories. Is something traveling between the particles or not? Is information moving or not? These questions assume that the only way to maintain consistency is through transmission. Quantum physics offers another option. Consistency can be global rather than local. Relationships can be fundamental rather than derivative. Einstein's unease was an honest response to a genuine shift in perspective. He recognized that something profound was being claimed, and he demanded clarity. Over time, that clarity has grown, even if the picture remains unfamiliar. Entanglement does not abolish space. It does not allow signals to outrun light. It does not turn the universe into a chaotic web of instant influence. It reveals something quieter. Across any distance, the quantum world can maintain relationships that are stronger than separation, ensuring that when outcomes finally appear, they do so in perfect agreement with a structure that was shared all along. There are few images in science as famous or as persistently misunderstood as a cat sealed inside a box. It appears again and again in explanations of quantum physics, often presented as proof that the universe is absurd, paradoxical, or deliberately mischievous. A cat, the story goes, is somehow both alive and dead at the same time, suspended in a strange limbo until someone opens the lid and looks inside. It is memorable, unsettling, and almost always presented as a literal claim about how reality behaves. That is precisely why it causes so much confusion. The scenario involving the cat was never meant as a statement about the world. It was a critique, a carefully designed objection meant to expose a problem in how quantum ideas were being interpreted. Schrödinger did not introduce the cat to celebrate quantum strangeness, but to question how far certain explanations could reasonably be pushed before they stopped making sense. To understand what the thought experiment was actually targeting, it helps to return to the unease that motivated it. By the early 1930s, quantum mechanics had already proven its power. It described atoms with remarkable accuracy, predicted spectral lines, and explained how light and matter interact at small scales. Experiment after experiment confirmed its predictions. And yet, despite this success, something about its interpretation felt unfinished. The mathematics described smooth, continuous evolution. Measurements produced single, definite outcomes. Somewhere between those two facts sat a gap that had not been fully explained. Quantum systems could exist in superpositions, carrying multiple possible outcomes at once, but measurements never revealed that multiplicity. They revealed only one result. What exactly was happening in between? Schrödinger was troubled by how casually this question was sometimes set aside. To make the issue impossible to ignore, he proposed an exaggerated scenario that deliberately stretched quantum reasoning into an uncomfortable domain. A sealed box contained a cat, a radioactive atom, and a device triggered by the atom's decay. If the atom decays, the device activates. If it does not, nothing happens. The atom itself can be described as existing in a superposition of decayed and not decayed. If that description is taken at face value and applied without qualification, Schrödinger asked, what does it imply about the cat inside the box? The discomfort produced by this question is not an accident. It is the entire point. Schrödinger was not suggesting that cats genuinely exist in such states. He was showing that something had gone wrong in the way the theory was being interpreted. The cat is not the claim, it is the warning. Much of the misunderstanding comes from blurring the line between measurement and knowledge. It is tempting to imagine measurement as an act of awareness, as if learning the outcome somehow causes it to happen. Open the box, see the cat, and reality snaps into place. This framing feels intuitive because it mirrors human experience, but it does not reflect how quantum physics actually works. Knowledge is not a physical process. Interaction is. Long before anyone opens the box, the system inside is already interacting relentlessly. The radioactive atom interacts with its surroundings. The triggering device interacts with the air, the walls, and itself. The cat interacts continuously with its environment, producing heat, motion, sound, and countless microscopic disturbances. These interactions matter because they entangle the system with its surroundings. As this entanglement spreads, the delicate superpositions that can exist in carefully isolated quantum systems become distributed across many degrees of freedom. The different possible outcomes become tied to different states of the environment. Once that happens, maintaining a coherent superposition is no longer possible in practice. The outcome becomes definite not because someone knows it, but because the system has become irreversibly linked to the world around it. By the time the box is opened, the result has already been settled by physical processes,